All right, it is 10, so let's get started. So remember, next week, Monday, is test number 3, and just some things about that. First off, the PowerPoint we're going to do today is the last one for test 2. Or sorry, test 3. So all the stuff we covered today. And just looking over what we still have to do today, there's no new PowerPoint for today, if you haven't noticed that. And so what happened and what I'm going to be doing this afternoon is no reading guide Wednesday. I'm going to use Wednesday to catch up. So no reading guide for Wednesday. And we'll just pick up what we were supposed to do today, and we'll do that on Wednesday, and it will all go from there. So next week, test 3. So be sure to be on the lookout for that. As always, the material that will be on test 3 is in the in-class test 3 folder. No surprises, hopefully, at this point in the semester, since you've seen how I do 2 tests. Test 3 is going to be more of the same. All right. With that out of the way, let's pick up right where we left off on Friday. And we were talking about how to calculate enthalpies of reactions. And we're doing constant pressure calorimetry, more or less. And remember, just as a little reminder, to find the delta H, or the enthalpy, or the change in heat of a reaction, what we do is we measure the change in temperature of our solution. If here we are dissolving salt, because Q reaction and Q solution are the same number, just opposite signs. And if you are under conditions of constant pressure, the heat of the reaction, which is Q, is equal to the enthalpy of a reaction, which is delta H. Again, don't get too hung up on the differences between enthalpy and heat at this point of chemistry. We're just mainly focused on introducing those words and looking at some calculations with those. So that's where we left off on Friday. So we're going to jump right back into a problem that deals with delta H. And that's question 3 from our Friday PowerPoint here. So question 3 says, you have zinc, and zinc will react with hydrochloric acid according to this reaction, where you have zinc and 2 moles of HCl makes zinc chloride and hydrogen gas. So let's say you put 0.103 grams of zinc. You can combine that with enough HCl to make 50 milliliters of solution in a coffee cup calorimeter. You're going to assume all the zinc reacts and the temperature of the solution goes from 22.5 C to 23.7 C. I want you to give me delta H for this reaction if the density of the solution is given there and the heat capacity is 4.184. And tell me, was this exothermic or endothermic? So we're going to begin there to refresh your memories. The equations you need are right here. So as always, make sure you go through here, look at your variables. Remember, delta always means final minus initial. If you get stuck or have questions, please send me a message, let me know. Otherwise, I'm going to give everybody a few minutes to work through this on your own before I solve it. And we'll do about 1 more minute here before I start going through it. All right, so hopefully you're able to start filling your variables and get part of the way through the calculation. So let's take a look at this. And this is basically the same problem we did at the end of Friday. So the first thing we need to do is figure out how much heat. Remember, when we're talking about heat or energy, it's always in joules. But how many joules of energy did our solution either absorb or release? And since the temperature increased here, that means the solution absorbed it. So when we're doing this, remember mass is mass of solution, right? You might be tempted to put the mass of zinc there, but that is not the mass of the solution. So we made 50 mils of solution. And the density of our solution is 1.03 grams per mil. Mil at the top, mil at the bottom, mils cancel out. And the mass of our solution then, it's 51.5 grams. So that's M solution. CS solution is given in the problem, 4.184 joules per gram centigrade. Delta T, final minus initial. So that is 23.7 minus, what did I write there? 22.5, which is 1.2 degrees centigrade. All right, so we have mass, CS, delta T, and we're ready to do some calculations. So Q reaction, which is what is the left side of our equation, basically. That's what Q reaction is equal to negative Q solution, which is mass, 51.5 grams, multiplied by CS, 4.184 joules grams centigrade. Grams at the top, grams at the bottom, grams cancel out, multiplied by 1.2 deltas, or degrees C cancels out. Our final unit is in joules, which is what we want because we're talking in energy, so that's good. And the heat of this reaction is negative 258.571 joules. What this means is that when we reacted 0.103 grams of zinc with hydrochloric acid, it released 258 joules of energy in the form of heat. That's why our solution warmed up. Since we're releasing heat, this is exothermic. On Friday, we did an endothermic reaction where the temperature cooled down of our solution. Here, our temperature is increasing, so it's exothermic. However, the answer that I want should be kilojoules per mole. Right now, our solution's just in joules. So we need to get it in kilojoules per mole. So let's figure out how many moles of zinc is 0.103 grams. Because I'm going to take that mole and divide it by my joules. So 0.103 grams of zinc. Looking at the periodic table, I can convert from grams to moles. So there are 65.38 grams for every 1 mole zinc. grams cancel out. So the number of moles of zinc I had in this reaction are 0.001575 moles. So I can take this number, my moles, divide it. So take my energy and divide it by how many moles I have, and you'll get an answer in joules per mole, which is 164,130 joules per mole. And then all we need to do there is convert from joules to kilojoules. So for every 1,000 joules I have, that's 1 kilojoule, which is negative 164.13 kilojoules per mole. Then my sig figs is going to be, my delta T is going to tell me my sig figs because that's only 2 sig figs. Everything else was 3. CS was 4. So this answer should be in 2 sig figs. So that's negative 1.64. Oh, sorry, negative 1.6 times 10 to the second kilojoules per mole. And that should be your answer, 1.6 times 10 to the second. And that's how we can work out one of these delta H equations where we dissolve a solid. Here we're dissolving an acid, but you dissolve a solid. You figure out how much solution you have. You figure the weight of the solution. And with the temperature change of that solution, you can figure out the enthalpy of a reaction. So it's exothermic because it's negative. Yes, the system is losing heat. That is correct. You got confused how I got 164,130. All right. So so you followed how we got Q reaction, right? So you followed how we got negative 258.571 by doing this equation up here. So what I did there is I got that much energy from dissolving 0.103 grams. So if I want to know the question I'm really asking is how much energy would I get out if I dissolved 1 mole of zinc? So to do that math, you take the energy you got from 0.103 grams of zinc, which is this number, divided by how many moles is 0.103 grams. When you do that, you get an answer in joules per mole. Right? I'm just dividing how many moles of zinc you had. That's it. Because that would be in moles and my denominator needs to be in moles. So that's what was going on here. 0.103 grams of zinc, then molecular weight of zinc to get moles of zinc. Divide Q by moles of zinc to get joules per mole. And what was only 2 sig figs? That is delta T. Delta T 23.7 minus 22.5. That answer is 1.2. So that is 2 sig figs. So my answer should be 2 sig figs. Everything else, well, the mass of my solution was 3 sig figs. The mass of zinc was 3 sig figs. CS is 4 sig figs. So that's my limiting sig figs. You should always be aware. So the question is, should we always remember to do all the equations separately to see all the sig figs? Because I was just looking at it all together. So when you're doing multiplication, division, addition, subtraction, what have you, always be aware when you do that, what sig figs you should get out, right? Normally when I do this, I will just make little notes like this and say, oh, that's 1.2 is 2 sig figs. And I only look back at that when I'm done. when I'm finished with the problem, then I'll go back and see what was my limiting sig figs. Yeah. So you should always be aware every time you do addition, subtraction, multiplication, division, you should always be tracking how many sig figs your answer is, especially in these type of problems where we do one calculation and then we use that in another calculation and then we use that in another calculation. You just have to be keeping track of your sig figs. And I just do that by writing up myself a little note. Yeah, so 23.7 minus 22.5. It is tempting to think that is 3 sig figs, but when you actually do the math, the answer is 1.2. Yeah. All right. Any other questions about doing a delta H enthalpy question like this? I know it's rather involved here, but hopefully step by step, it's not too bad. You got 164,172.1905. I mean, at the end of the day, you get the same answer as I do when you go to sig figs, so I wouldn't really matter. If like on a test, if my answer is 164,130 and you got like 164,172, usually that would tell me that it's just due to sig figs, because that's like 0.0001% difference. It's not that big of a difference because we're talking about hundreds of thousands. So I wouldn't really concern yourself too much about that level of error. I think on the questions on the test, I automatically have the computer say if you're within 1% or something like that, you get full points. And then usually I go and manually check them anyways because I don't trust the computer to do it accurately. But if there are no other questions, we can move on then. And let's talk about relationships that have to do with enthalpy. So enthalpy is what is called extensive, the enthalpy of a reaction. That is, the more stuff you have, your enthalpy will change based on the amount of stuff, which makes sense if you think of enthalpy as heat. What will generate more heat? 1 stick of dynamite or 100 sticks of dynamite? Well, 100 sticks of dynamite generates a lot more heat than 1 stick. And so when we talk about change in enthalpy of a reaction, we call that an extensive property. So extensive properties means it depends on the amount of stuff. Conversely, if you ever look at an intensive property, intensive mean it doesn't matter how much stuff you have. An example would be color, right? If you have 1 gold brick or 1/10 of a gold brick, the color is the same. So color is an intensive property. And since the change in enthalpy of a reaction, remember, anytime you see delta, read that as change of, so change of delta H or change of H in a reaction. Since it's extensive, we have some rules that will govern how delta H changes. The first is multiplication. Let's say we have a reaction. Carbon plus oxygen makes carbon dioxide. The change in enthalpy of this reaction is negative 393.5. If you multiply this equation by 2, which is going on here, we just multiplied everything in that equation by 2, the enthalpy gets multiplied by 2. As seen in this example problem, A plus 1/2 B goes to C. If the change in enthalpy there is X, what is the enthalpy change for the reaction 2A plus B goes to 2C? Well, we just multiplied everything by 2 to go from the top to the bottom. Therefore, the change in enthalpy in this reaction would be 2x. And this is our first relationship of enthalpy. When you multiply your equation by some number, the change in enthalpy is multiplied by that same number. It's the same with division too. Going backwards, right? If I have everything and I divide it by 2, you just take your delta H and you also divide it by 2 as well. So that's our first relationship of enthalpy. Our second relationship is what happens if the reaction is reversed. So here we have carbon plus oxygen goes to carbon dioxide. Delta H there is negative 393.5. But let's say we wanted to do the reverse reaction. Let's say we wanted to take carbon dioxide and break it down into carbon plus oxygen. Since these reactions are just reversed, we took the product and made it a reactant, we took the reactants and made it a product, all we do here is change the sign of delta H. So at first it was a exothermic reaction to create carbon dioxide. Therefore, it must be an endothermic reaction to break it down. You get heat out when you create carbon dioxide, so it makes sense to break it down, you have to put heat in. Opposite and equal. Opposite but equal. Yeah, that's what it should be. So let's say A plus B goes to 2C. That is an enthalpy change of X. Well, what if we had the reaction 1/2 B plus C goes to 1/2 A? So here we are doing our reversal. So we know if this was a positive value, this should be a negative value. And we took this and we divided it by 1/2. We took all the numbers, or sorry, not by 1/2, by 2. We divided it by 2. So 2C became 1C. 1B became 1/2. So this should be negative 1/2 X. Because you can either think of it as dividing it by 2 or multiplying by 1/2. Either way. Why is it negative? Because the equation flipped. It was A plus A goes to B plus 2C. Now I'm saying what's B plus C goes to 1/2 A. So my first reaction, my products were B and C. My second reaction, those are my reactants. So since I'm flipping the equation, you flip the sign. H1 was positive, so H2 has to be negative. That makes sense? No, dividing and multiplying has nothing to do with the sign. If you divide something, you don't change the sign. If you multiply something, you don't change the sign. You only change the sign when you flip the equation, when your products become your reactants. So another example without the multiplying, A goes to B, delta H is 10 kilojoules. Therefore, B goes to A, delta H is minus 10 kilojoules. Then if I said, well, 1/2 B goes to 1/2 A, delta H would be negative 5 kilojoules because I divided it by 2. Oops. And if I said 3B goes to 3A, that would be negative 30 kilojoules because I just took that and multiplied it by 3. So would it either be negative 1/2 X or minus X divided by 2? Yep, those are the same thing. 1/2 times X or X divided by 2. A lot of the same thing. Yep. Any other questions about our delta H relationships here? Which I have summarized more or less right here. And then you could say like 10A goes to 10B. Delta H is 100 then. 10 times 10. All right. That's a positive 30. No, that's a negative 30. Because A goes to B is positive. Therefore, anything that's B to A is negative because I flipped it. Right. That's what I mean by flipping. What was a product? Now it's a reactant. What was a reactant? Now it's a product. Right. So let's get some hands-on practice then. Consider a reaction of generic molecules. A plus 2B goes to C plus 3D. Delta H is 155. Therefore, for every other scenario, A, B, and C, tell me what delta H is. So I'll give you a couple minutes to figure this out. Then I'll be back with the answers. If you have questions, let me know. All right. So let's take a look at these. So A, the only difference between our original problem and A is that we're multiplying all of our moles by 3. Therefore, delta H is simply our original value multiplied by 3. So 155 multiplied by 3 is 465 kilojoules. And B, the difference between our original problem is we flipped it. So C plus 3D was a product. Now C plus 3D is a reactant. When you flip something, all you do is change the sign. So that's negative 155 kilojoules. For C, we not only flipped it, but we divided everything by 2, or we multiplied it by 1/2. Either way. So when you divide something, well, first, since we flipped it, it should be a negative because this was a positive value. And we divided all of our moles by 2. So we just take delta H and we divide that by 2 as well, which would be negative 77.5 kilojoules. So that's how, if we know one equation, the change in enthalpy, we can predict the change in enthalpy of any related equation. If you multiply the amount of stuff, if you divide the amount of stuff, or if you have the reverse reaction. All right, now seeing that and getting an ability to try it, any questions about that? All right, let's go to our next relationship then. So here we're doing something a little more complicated. So I have a reaction. Calculate delta H for Fe2O3 plus 3CO goes to 2 iron plus 3 CO2. And here I give you 2 half reactions. So the last relationship we have to go over is that delta H's are additive. What I mean by that is, let's say the reaction A to B, that is delta H of 10 kilojoules. And let's say that B to C, our reaction of a B molecule going to the C molecule, that delta H is negative 2 kilojoules. Therefore, the reaction A going to C, which is these 2 reactions added together, because when you add these reactions together, you get A plus B goes to B plus C. You're literally just keep the reactants on the same side of the arrow and the products at the same side of the arrow. And if you have the same molecule on each side, they cancel out, just like how we did for our net ionic equations, right? If you had something on each side of the arrow, they would cancel out. That's what's happening with B here. So we have A plus C. And to figure out that delta H, you just add your delta H's together of the equation that made it up. So delta H here would be 8 kilojoules, because I'm just adding these 2 reactions to make a new reaction. So here, what we're doing is I give you 2 half reactions, or I should stop saying half reactions or not half reactions. I give you 2 reactions. I want you to manipulate these reactions, like flip them, multiply them, do whatever you need to do, so that when you add these 2 together, your final reaction looks like this. And I want you to tell me what the delta H of this reaction is, given this information. So this is definitely like a puzzle to try and figure out how to combine these 2 reactions to get this. So I'm going to give you a couple minutes to try and struggle through that. And then I will show you the way. But if you do have questions, get stuck, let me know, and I can help you out. So question, are we individually making the two reactions look like the first or combine both of them into one big reaction to look like the first? You are combining them to make it look like the first. That is the only way you can make it look like the first, because if you look at our reaction, it has carbon dioxide in it, and just our first reaction does not have carbon dioxide, but our second reaction does. So you're going to want to add them together. All right, so we're playing the game. How can we combine the two bottom reactions to look like the top reaction? So let's just start with the first reaction and see what we have to do. So in our target, Fe2O3 is a reactant. Remember, these are reactants. And in our reactions that we want to combine, it's a product. So that's a problem. We need to change that. We need to make Fe2O3 a reactant to match our target. So I can do that. I can just flip the equation. There's nothing wrong with that. So I'm going to flip this equation to say this. And remember, when you flip an equation, the sign of delta H changes. So it was negative 824.2. Now it's positive 824.2. And since I have in my target 1 mole, remember, if there's nothing there, if there's no number, that number's a 1. I have 1 mole of Fe2O3 in my target. And in the things I need to combine, it's at 1 mole as well. So I don't want to multiply or divide this by anything. So I'm going to leave my top reaction alone for right now. I think that's good. Let's look at my bottom reaction. I have carbon dioxide as a reactant in my example here. And in my target, I have carbon monoxide as a reactant as well. That's good. They're on the same side of the arrow. However, I have 3 moles here and only 1 mole here. That's a problem. But I can multiply it by 3. That's no issue. So I'm going to take this equation, our bottom equation, and multiply it by 3 to get 3 moles of CO gas plus 3/2 O2 goes to 3 CO2. And when you multiply an equation by a number, delta H is multiplied by that same number. So the enthalpy change for this reaction is 282.7 multiplied by 3, which is negative 841 or 848.1. And now I should be in a position to combine these, because my top reaction, I already said I don't want to mess around with it anymore. My bottom reaction, the moles are good. The position of the elements are good. I don't want to mess with that either. So let's combine them. So you keep all your reactants together on the same side. So Fe2O3 plus 3CO plus 3/2 O2 goes to, then you keep your products on the same side, 2Fe plus 3/2 O2 plus 3CO2. You check to see if there's any elements that are the same on both sides of the equation. And we do, we have O2. And they have the same number of moles, so they cancel out completely. If it's on both sides of the arrow, then they destroy each other. So our final reaction is Fe2O3 plus 3CO goes to 2Fe plus 3CO2, which is exactly what we wanted in our target. And then all you do, since we added equations, you just add the delta H's together. So this is 824.2 minus 848.1. I put a negative sign here, but it's really plus a negative, so minus, which is negative 23.9 kilojoules. That should be your answer. Any questions? Those of you who like puzzles, maybe you'll enjoy problems like these. Those of you who hate puzzles, I say why puzzles are great fun. How did I get negative 848.1? So in my bottom equation here, I need to multiply that by 3 because, like I said, I have 1 mole of carbon dioxide as a reactant, but in my target, I have 3 moles. So I multiplied this reaction by 3 to get 3CO plus 3/2 O2 goes to 3CO2. When you multiply a reaction by a number, the delta H gets multiplied by that same number. So that 848.1 is simply 282.7 multiplied by 3. That's what I did there. Right. Any other questions? All right, let me just see how much more of this PowerPoint we have. All right, we have 2 more questions. So question 6 and question 7 we'll do on Wednesday, and these will be on the test, question 6 and question 7. So everything on this PowerPoint is on test 3. Then on Wednesday, after we get done with question 7, I'll move on to a new PowerPoint. That new PowerPoint won't be on the test, but that'll be, yeah, I'll explain that again on Wednesday, and they'll be in separate folders. So hopefully that'll be clear. Otherwise, that's the end of today. I'll put a homework up so you can get some more practice on these types of problems. And hopefully I will see you on Wednesday. Have a good rest of your day.